Okay, so now is the time to go into nonlinear scalar conservation laws, which is really the motivation or the first type of systems we are going to look at in the context of finite volume schemes. So we are going to first introduce conservation laws. And scalar conservation laws is the simplest type of conservation laws out there. And then we are going to introduce finite volume in the context of scalar conservation laws. And then we are going to upgrade our analysis to system of conservation laws and how to use finite volume schemes to solve them. In finite difference, we've been looking at like second order schemes all the time, and it is not that difficult to construct higher than second order schemes. But it turns out for conservation laws that are nonlinear and have things like shock waves, going to second order is a big deal. Okay, and so we are going to discuss how to go to second order schemes. And then we are going to discuss how to solve 2D and 3D problems, including unstructured grid using finite volume. All right. Okay. So let's first introduce what is conservation laws. Conservation laws are the type of partial differential equations that describes a kind of physical systems that quantities are conserved. Like, for example, in fluid dynamics, the amount of mass is conserved. No matter where the flow goes, the mass is basically moved from one area to another area. The total amount is conserved. If you draw any control volume, the amount that goes in has to either accumulate within the control volume or goes out somewhere. That is conservation. Or energy is conserved, right? If you draw a control volume, the amount of energy you add into the control volume, either through putting energy through the boundary or like using lasers or something to heat it, it's either going to accumulate in the control volume as kinetic energy or internal energy, or goes out of the control volume somehow. This is also conservation. Also there is conservation of momentum. Right, any force you put on the control volume through pressure or through gravity or anything either accumulates as momentum or goes out. This is also conservation. And in previous years, we have done like an interesting project on traffic flow on highways. What is the conservation there? Conservation there is the number of cars on the highway is conserved, right? It'd be a bad thing that like cars disappear or something. But like the amount that flows, if you draw a control volume, which is a segment of the highway, the number of cars flow in is equal to the amount that goes out plus the rate of accumulation of cars or the increase of the density of the cars within that segment. So these are typical examples of conservation. How to write it down mathematically? If you draw a control volume, let's say omega, okay, how do you express? And we usually express the conservation in terms of density, rho. Okay, rho is the amount of stuff. I use stuff because it can be mass, it can be energy, can be a certain, it can be moles if you are looking at a certain species of, it can be momentum per unit volume. And we are looking at per unit volume here, not per unit mass or per unit other thing. We are looking at per unit volume because we are looking at differential equations. We need derivatives in space, and space is the important thing to have. Okay, so the total amount of stuff within this volume is integral over omega rho times dx. All right. Conservation says that the derivative of the total amount is zero if there is no influx or outflux through the boundary. If there is no source terms like chemical reaction that increases the energy or increase the number of moles within that volume, right? So if there is an inflow and outflow through the boundary, that can be also accounted. That is equal to integration only over partial omega, which means the boundary. So this boundary is partial omega. That's a convention that basically represents the boundary points of a set. Okay, integration over the boundary of a certain flux. Let me write it as F times. I mean, flux usually has a direction because it usually is either in or out, or it can be in the tangential direction, which doesn't contribute. So the flux needs to be dot product with the surface normal. If it's positive, if the dot product is positive, that means inflow, right? Okay, so if this thing is positive, that means inflow. So and the normal direction is usually outside, so we need a minus sign here. So that means if the dot product is positive, that means outflow, and that contributes to the decrease in the total amount of stuff inside the volume. If the dot product is negative, that means inflow. That contributes to the increase in the amount of stuff. That is integrated over the surface of the control volume. And let's also think of potentially a source term. The source term can happen inside. For example, in energy conservation, it can be like from chemical reaction. It can be from radiative heating, which basically shines from something outside. This thing usually doesn't exist in mass conservation. It's hard to think of a source term for mass. But let's say this is S times dx. All right, this is a source term. So this is a typical form of a conservation law. And the conservation law can be usually written as a differential equation if you can represent both the flux and the source term as a function of rho. Okay, if you can represent F as a function of rho, if you can represent S also as a function of rho, then it becomes an equation you can solve. And the unknown is going to be just a rho. In scalar conservation law, which we're going to study today, rho is a scalar function of space and time. In the system of conservation laws, the rho can be multiple functions of space and time. In fluid dynamics, in the famous Navier-Stokes equation, rho includes three things. It includes the density of mass. It includes the momentum, or the density times velocity. That's the momentum. I mean, actually, momentum is three fields. It's a vector field. It's not a scalar field. And also, it includes the energy. Okay, so that forms a system of conservation law. But today, let's study scalar conservation laws. So you may be asking, this doesn't look like a differential equation at all. It's more like an integral equation, right? But it is actually a differential equation. It is a differential equation because of a theorem called the Gauss's theorem. Gauss's theorem basically says, who has seen this Gauss's theorem before, like in vector calculus? A divergence theorem, yeah. Okay, so who have seen this before? Almost everybody. Okay, so I'm going to write it down very briefly. So the divergence theorem says that the integral of the divergence of a field, I'm just going to write it f, over any control volume, can be represented as the surface integral of f dot with n ds. All right. So we can immediately see the application in this conservation law. Is the surface flux doesn't have to stay as a surface flux. It can be transformed into a volume integral of the divergence. So this thing is equal to minus volume integral of the divergence of this f dx. And then look at this equation. This equation basically says that, okay, oh, by the way, you can take this ddt inside the control volume because the control volume, the omega, stays the same over time. We are having a fixed control volume, so you can take ddt into the control volume. So now if you look at this equation, that basically says that the integral over the control volume of multiple terms, d rho dt, well, because rho is a function of also space, so we need to convert it into partial derivatives, plus everything, I'm writing everything into a spatial integral, and also minus s over dx is equal to 0, right? That's another way of writing exactly the equation up there. I'm just combining all the integrals of the same thing. And what's more interesting is that this has to hold for any omega. It just doesn't hold for a omega. It holds for any control volume we can draw. What does that mean? That means the integrand, as long as it's a continuous function, it has to be equal to 0 point-wise, right? If it's not equal to 0, at any point I can draw a tiny control volume around that, and the integral is not going to be 0.